This circuit is nothing but this circuit with a gate and a drain shorted at the same points. This VDD common rail is connected like a battery, like this, through the resistor and then to the common point D, where the drain and the gate are connected. The current, the ID that we are asked to find, the current that flows through the drain, starts from the battery VDD and goes like this. Note, the current does not flow inside the gate over here. Why? Because the voltage is constant, and even if it was of a small frequencies, still we would assume that it doesn't flow like this. Only higher frequencies. This is a model for another course, another class. Don't worry about it for now. The current flows like this through the source and then again does this circle through this loop. Now, for us to find how much the current is for the case where we have channel length modulation and when we don't have channel length modulation, we'll start with when we don't, and we are going to take the equation from theory of the current from when we have saturation. All right, we assume we are in the saturation region. We assume this is how we normally work. We assume we're in the saturation region first. We do everything, all calculations, and then we verify that we are in the saturation. And if we are not, we return and take the equation for the triode region. All right. I now assume we are in the saturation region. I take the equation IDs 1 over 2 mu n C ox W over L VGS minus VTH. I'm given some values for the MOSFET over here, so I'm given enough of them to know how to handle this. Now mu and Cox, I know how much it is, W over L I know, VTH I know, I'm given it, it's 0.4, and now I have two unknowns, ID and VGS. How much is VGS? Well, I'm going to first name this loop as loop 1, alright? And I'm going to find this VGS and this VDS in comparison to other values of the circuit that I know. So I'm going to do a KVL on this loop over here, and I'm going to say that VDD, this battery, all right, this voltage, because the loop goes like this, because I enter a negative terminal, this VDD is going to be on this side of the equation, and then every other time that I enter a positive terminal, I'm going to put it on the other side of the equation. Because the current that I have shown like this is going through the same direction as the loop, RD supposedly has the positive terminal from which the current goes in, all right? Maybe it's a bit strange. If you remember from circuit theory 1, this will be very clear. So current flows inside the resistor, and if you don't remember it, it's okay, time to refresh your memory. So this is supposedly to be the positive terminal over here, IDRD from this side of the equation, plus VDS. VDS is VD minus VS, so it enters the positive terminal, all right? But I also note that VDS is the same as VGS. Why? This is a unique property of the diode-connected device. The gate source and the drain source have the same voltage difference because this point is common. So the gate point over here is the same as the drain point over here. So it is VD minus VS is the same as VG minus VS because this VG is this VD minus the same VS. All right. Now, taking all of these three equations, I do the math over here. Now, I could have replaced VGS with VDS and then solve in relation to the current and have an equation here of only currents, all right, with the current being the only unknown. However, instead of using the currents over here, I use them VDS as an unknown, and why it will be clear later. But for now, I'm going to do it like this, and find the current later. Alright, so I replace everything over here. Alright, this current is VDD minus VDS over RG. I replace it over here. VGS is the same VGS. VGS is VDS. Alright, so I replace everything. I know very carefully. VDD is 1.8 volts. RD is 1 kilo ohms, so 10 to the power of 3. Mu NCOX is micro amps. Alright, so I'm also very careful to scale this properly. I replace everything else and I have nothing but a quadratic equation over here. If you solve this, is a typical quadratic which has two unknowns. 0.82 as a result, sorry, two roots, alright, two solutions. 0.82 minus 0.2, which is the accepted value. Well, I have to now that's the reason we did it like this. I have to check the saturation. So the saturation conditions are as follows. VGS must be more or equal than VTH, and VDS minus VGS must be more or equal than minus VTH. Alright, which means that VDS must be more or equal than VGS minus VTH. Now, since VDS and VGS are the same, this and this give me 0. Alright, so this is 0, it's higher than minus VTH, which is 0.4. Alright, which is true. So this holds true always for the diode-connected device, but this does not. This is not always true. So we check that with this value, with 0.82, this holds true always. So this is rejected, all right, and 0.82 is accepted, which means that VDS is 0.82, all right. And now that VDS is 0.82, I go back and replace the value over here, and I have an ID of 0.98 milliamps. All right, and that's it. Wasn't that hard? The difficult part was to understand that over here we have to replace with the VDS instead of the currents, just so we go ahead and check the saturation conditions and then go and replace on the current itself. All right, so this is finished. For the case where we have channel length modulation, pretty much do the same thing over here, all right, up until this point, with the only difference being that we are going to add this term for the current, since this is the correct equation from theory for the channel length modulation. Obviously, VDS and VGS are the same, all right, so this is going to make us our life much easier. However, when we try and solve this and we replace the numbers, the problem becomes clear. We now don't have a quadratic equation as before, so with the inclusion of channel length modulation, things get very complicated very quickly. We now have a cubic level polynomial, which can be solved using Cardano's rule or anything like that. You can try to solve this like this, but this is not a reliable way to do this, because when these circuits become very complicated, you will not be able to do a standard rule like this, all right? And of course, you are not going to remember in your exam how to do these complex solutions for the cubic equation. What you are going to remember, however, is the following methodology. This is the repeating method, all right, where we repeatedly go and check a value for the VDS in this instance. We keep replacing and trying new values for this VDS up until the point where this equation and this part of the equation are giving us the same value. So I try using the case where we don't have channel length modulation, so 0.82. If my exercise didn't ask me for the channel length modulation case for when we don't have it, I would go and do it anyways, just so I have a reference value for the voltage. Now, I go ahead and try to replace 0.82 in this equation, and I have that this part of the equation is 0.98, and this part of the equation is 1.06. This is larger than this, alright? This means that I'm a bit off. Now, next step is to take a slightly smaller value. So this is a good rule to remember, that when you have channel length modulation, the voltage at the drain source is going to be slightly less, alright? Than when we didn't. So I'm going to try a slightly smaller value. So this is going to be 0.8. I try 0.8. Now this part of the equation is 1, this part of the equation is 0.96. So this is larger than this part, alright? This is larger. This is good. It means that my solution will be somewhere in between this and this value. If it was still smaller, I had to go even an even smaller value for VDS. Alright, now I test the value between these two. I test this value, 0.81. How much is the left side? 0.99. How much the right side? 1.01. It is smaller, which means the solution will be between 0.81 and 0.8. Alright, I test a value in between, alright, 0.805. This methodology is similar to the divide and conquer, if you know from algorithmic theory. Anyway, the left side now is about 1, the right side is 0.99. As you see, we get closer and closer with each iteration, which is good. And now I'm going to test another value, which will be between this and this point, alright? Going to check 0.807, and finally I have that the left side is equal to the right side. Note, my accuracy here is for up to 2 decimals. In reality, the exercise will ask you, give me a solution for up to 3 decimals, 4 decimals, etc., or 2. But if it doesn't, we have to pick a reasonable value, alright? I pick 2 decimals for now. And to make this solution much faster, alright? I could keep going on and on and on up until I have 3 decimal accuracy. Alright, now I have a value for the VDS, which gives me a reasonable accuracy. Alright, I take this value, I check, is this higher than VTH? Yeah, it is, so my saturation conditions should be satisfied. Alright, should be satisfied. This is always, we said that it is always true. This is satisfied, alright, VDS is the same as VGS, which is higher than 0.4, alright. So now I know I'm in saturation. I go ahead and replace VDS inside here, same as VGS. I solve for the current and I have a new value for my current, which is 0.99 milliamps, which is slightly larger than when I didn't have channel length modulation. So we see that whether we have to include or we don't the channel length modulation, the difference on this voltage will be perhaps small or large depending on the context. So is 0.82 so much larger than 0.807? Is 0.98 milliamps so much smaller than 0.99 milliamps? Well, it always depends on the context of the circuit. So if we have other values here that are sensitive to these small changes, of course, we would have to take into account channel length modulation. If there wasn't, We wouldn't. All right? Okay, and this was the diode connected device, the MOSFET connected like this, and it wasn't that difficult to solve this because this VDS and VGS relationship makes our life much easier, all right? Knowing that these two are pretty much have the same value. All right, that was for today. Click over here for the MOSFET playlist for more MOSFET exercises or MOSFET basics if you have trouble with this. Anyway, study well and take care, boys. Bye-bye.